Hello and welcome everyone. Welcome back to the second session of this webinar on applications of remote sensing based evapotranspiration data products for agricultural and water resources management. Last week we had a presentation and data demonstration from Forrest Melton. He focused on OpenET, the product based on multiple satellites and multiple models. It's an ensemble product. And this product was a regional product. It is available over the Western United States. As Forrest mentioned, it will be extended to the entire US in about a year or so, and it will be extended to other countries as well as more in situ data become available in other countries. Today the focus is going to be on the ECOSTRESS ET product, which is a global product. ECOSTRESS is relatively a new sensor. And we have a guest speaker today from NASA JPL, Gregory Halverson. He is going to focus on how to access data, ECOSTRESS ET data, how to subset it and analyze it in great detail. Then next week we have exercises where we will also go through some of the steps to get OpenET data and ECOSTRESS ET data. So we'll start with a very brief introduction of ECOSTRESS today, and then Gregory Halverson will have the demonstration of data products and analysis. Just to make one point of clarification is that the demonstration that you will see from Gregory Halverson, if you wish to replicate that, then these are the steps required. You're required to create a NASA Earth Data login as a new user if you are not already a registered user, and that is required to download data. Then download and install the latest version of QGIS. Download and install Anaconda, and download and install Visual Studio Code. So these are the links. Now, it is not required for you to replicate these steps now or for this training. This is mostly for your information and reference. A recording of this demonstration will be available within 48 hours on our website. So later on, or whenever you need to follow these steps, or to analyze ET data, you can follow this demonstration, use these softwares, and do the analysis. So again, to clarify, this is mostly for your information and reference. There will be a homework that will be posted next week on June 15th. And those of you who complete the homework by deadline and those of you who haven't attended all the live webinars will receive a certificate of completion. So just to talk about ECOSTRESS briefly, ARSET actually already conducted a webinar a couple of years ago on introduction to ECOSTRESS, and here is the link with a lot of very informative details. But just at a glance, the ECOSTRESS mission was launched in 2018 in June, and it started operations in August 2018. It was launched to the International Space Station, and it has a global coverage as we talked about. It was first mission to have Wi-Fi for a science mission, and it has raw product and many derived products. So all L1 to L products are available. And here's the website with more information about ECOSTRESS. One important thing to note here is that ECOSTRESS is on ISS, which has varying overpass time. So on different regions, it passes through different time of day, and so it samples diurnal cycle. And so ET from ECOSTRESS can have that leverage that it can look at different parts of diurnal cycle and how ET varies diurnally. And USDA actually uses that to fill gap between, say, Landsat data, which is 16 days apart. And so ECOSTRESS ET is quite useful to fill that gap in between. So these are, if you go through the webinar link that we just showed, you will be able to see a lot more applications and details about ECOSTRESS ET. So next we will have demonstration from Gregory Halverson. So Gregory has been at JPL since 2015 and he is a scientific application software engineer. He develops geospatial data processing software for remote sensing systems. And his current projects include a redesign of the ECOSTRESS product generation software. He also generates daily high-resolution remote sensing data fusion techniques, thermal stress on coral reefs, thermal habitat compression in the California Bay Delta, and evapotranspiration monitoring applications in the western states. So with that, we invite Gregory Halverson. So Greg, take it away.
Hello, I'm Gregory Halverson from the Jet Propulsion Laboratory. Welcome to our tutorial for using ECOSTRESS surface temperature and evapotranspiration to monitor agriculture. I would like to acknowledge my co-authors Carrie Cos-Nicholson and Christine Lee of the Jet Propulsion Laboratory. This research was carried out at the Jet Propulsion Laboratory, California Institute of Technology, under a contract with the National Aeronautics and Space Administration. Reference herein to any specific commercial product, process, or service by trade name, trademark, manufacturer, or otherwise does not constitute or imply its endorsement by the United States government or the Jet Propulsion Laboratory, California Institute of Technology.
We're interested in our ability to sustain food production. We're interested in our ecosystem health. And that's all tied to water. How much water our plants, our crops need, we want to know. And as water resources become more uncertain, more variable, we need to really track that really precisely. We can't just guess anymore.
So ECOSTRESS is going to measure the surface temperature, and then we're going to use that surface temperature to be able to determine how much water the plants that we're looking at are using.
We'd like to show how we can use ECOSTRESS data to optimize agricultural water use.
ECOSTRESS is an instrument that's going to go on the International Space Station. It stands for the Ecosystem Spaceborne Thermal Radiometer Experiment on Space Station.
It focuses on how much water plants use all over the planet and how much water plants need, and if there's stress, water stress or heat stress that plants are facing.
We can measure the surface temperature of the Earth within a few tenths of a degree, and then we can use that information to look at objects on the surface of the Earth, and in this particular case we're interested in looking at plants.
Plants, as they start to suffer from heat or water stress, they begin to heat up. In a similar way to a human with a fever. We can pick up that stress before the plant is visibly affected. So there's this window where water resource management and agricultural users can actually allocate more water before they die, before the damage is irreparable.
The space station is going to fly over at different times to be able to look at how the stress is changing through the day and allow us to characterize vegetation in ways that we've never been able to characterize it before. The instrument itself is looking down at the surface of the Earth, and it uses a mirror that rotates to scan across the surface. This measurement's being made in microseconds, but it's enough time for us to measure the energy that's coming off it and then translate that energy into a temperature.
The temperature measurements from ECOSTRESS can detect volcanoes. We can detect urban heat from cities.
So although we're focused primarily on looking at plants and making sure that we can maximize the amount of food that we can get back for the water that we use, the mission can be used for many other purposes. What hasn't been possible in the past is to make the measurements as frequently as we need to make them with sufficient detail, and it's that combination that is so important. And really that's just a reflection of the improvements in technology.
Our ability to sustain livelihoods, food production, ecosystems, and the health of the planet through ECOSTRESS data is invaluable.
To access ECOSTRESS data, we'll use the application for extracting and exploring analysis-ready samples, or APIRS. To use AppEars, open your browser and go to appears.earthdatacloud.nasa.gov. Once on the AppEars site, go to the Sign In button on the top right. If you do not already have an Earth Data login, you'll need to register for an account with the blue Register button. Once you've registered for an Earth Data login, proceed to log in to the AppEars system. Once you're logged into AppEars, go to the Extract tab on the menu at the top, and this will give you an option for area or point. Point extraction will produce a CSV table of points queried from ECOSTRESS images. This is good for comparing ECOSTRESS to ground data at points. Also on the Extract tab is the area extraction, which we'll use to request a time series of ECOSTRESS images. Once you're on the Extract Area Sample page on AppEars, go to Start a New Request on the left. Now that we're on Extract Area Sample, we need to select the spatial area of our request. We'll use the WebGIS map on the right of this page, and we're going to zoom in using the Zoom In button to Farmington, New Mexico on the northwest corner of the state of New Mexico. We want to explore ECOSTRESS surface temperature and evapotranspiration over agriculture in Farmington, New Mexico. To select the spatial area surrounding these farms, we're going to click on the Draw a Rectangle button on the bottom left of the map. And we're going to draw a rectangle surrounding the agricultural area. To search for ECOSTRESS products in this area, we're going to click in the Search for a Product box beneath Select the layers to include in the sample and type in ECOSTRESS. The first product we want from ECOSTRESS is the ECOSTRESS Level 2 Land Surface Temperature and Emissivity product. The surface temperature layer from this product is called SDS-LST. We'll click on the plus sign to add this layer to our request. Now let's look for other ECOSTRESS products by clicking the X on here and going back to search for a product. We would also like to request the ECOSTRESS Level 3 ET and Level 4 Evaporative Stress Index. Here is the ECOSTRESS Level 3 Evapotranspiration PTJPL product. We'll click on that, and we want to request the Total Instantaneous ET layer called ET-INST. Now let's search again for evaporative stress. Here is the ECOSTRESS Level 4 Evaporative Stress Index. And the Evaporative Stress Index layer is called ESI-AVG. For the surface temperature layer, we're also going to need a cloud mask. Here is the ECOSTRESS Cloud Mask product, and we want the SDS Cloud Mask layer. We need to select a date range for our request. For our first request, let's select the summer of 2019, starting from the beginning of July until the end of September. Down in the output options at the bottom of the page, we'll select GeoTIFF as our file format. And then in the search for a projection box, we'll select Native Projection. Before we submit our request, we need to give our request a name. We'll go up here and click in Area Sample Name under Enter a Name to identify your sample, and we'll put in our name. This area is Farmington, New Mexico, and we're requesting ET for the summer of 2019. To submit the request, we'll scroll to the bottom of the page and click on the blue Submit button. The request has now been submitted. Go to the Explore tab at the top. This lists our active requests. We can see that our Farmington ET Summer 2019 request is still processing. Now let's go back to our peers and check on the status of our request. To check our request, we'll go to the Explore tab at the top. We can see that our Farmington ET Summer 2019 request now has a status of done. We're now able to download our ECOSTRESS data. To download, we'll go to the Download button in the middle of the three blue buttons on the right side of the request. This page gives you a listing of the ECOSTRESS files available to download. We're going to select all the files by clicking the checkbox at the top left. And then we're going to start the download with the Download menu on the top right and click Download Files. Now that we've downloaded the files from our request, we should organize our project into a folder. Let's create a folder to hold our request files. These are raw files that we'll need to cloud mask and clean up. Now let's go back to QGIS and save our QGIS project in our project folder. We'll go to Project and Save and navigate to our project folder and give our QGIS project a name. Now in Project Home, we can see our project files. Now let's examine one of our ECOSTRESS surface temperature images by dragging and dropping it into QGIS. We can see the surface temperature of the farms in this image, but we can also see dark patches of clouds. We're going to have to cloud mask these ECOSTRESS images using Python. While we're waiting for a request to process, let's install QGIS. QGIS is a free and open source geographic information system, or GIS, that is cross-platform that anyone can use on Mac OS or Windows. To find QGIS, go to qgis.org and select the Download Now button. Download the latest release for your platform. From your downloads, run the QGIS installer. Now that we have QGIS installed, we need to install a plugin to use a base map. From the menu bar, go to Plugins and Manage and Install Plugins. In the Plugins pop-up, search for HCM GIS and select HCM GIS. Click Install Plugin. Now on the menu bar, there is an HCM GIS menu that will give you a selection of base maps. Let's use the Google Satellite base map. Moving around in our map, we'll use the plus and minus hourglass buttons at the toolbar to zoom in and out. Let's zoom in with the hourglass plus button. And we'll zoom in to our study area in Farmington, New Mexico. We can pan the map around using the hand button on the toolbar. To get started with Python, go to anaconda.com. Anaconda is a scientific Python package manager that we'll use to download the dependencies we need to process this raster data. At anaconda.com, click on Download to download the latest version of Anaconda for your platform. Once we have Anaconda installed, the first thing we're going to want to do is install the Mamba package. To install the Mamba package, we'll use the command conda install -c conda forge mamba. Once you have the Mamba package installed, we're going to use Mamba to create an Anaconda environment that contains the Python packages that we need for geospatial analysis. To create this environment, use the command mamba create. We're going to give our environment a name with -n, and we're calling it ARSET underscore ECOSTRESS. We're going to set the channel that we want Mamba to pull these packages from with -c and conda forge. And then we're going to list the packages we need, starting with Python itself, set at version 3.9, Jupyter, which will allow us to use Jupyter notebooks. Rio Xarray is the package we're using to open rasters, and hvplot is the package we're using to make maps. To run our Jupyter Notebook, we're going to use Visual Studio Code. For Visual Studio Code, go to code.visualstudio.com and download the latest version for your platform. Now let's open our project folder in Visual Studio Code. We'll go to File, Open Folder, and navigate to the project folder we created. Now we can see our project files in the Explore panel on the left. Now let's try cloud masking an ECOSTRESS Level 2 surface temperature image using the ECOSTRESS Cloud Mask in a Jupyter Notebook. First, we'll need to create a notebook. We'll click in the Explore panel on the left and click on the New File button. And we'll give our notebook a name. This file needs to end with the extension IPYNB. Now we've created a Jupyter Notebook. We want to make sure that the environment is set to the environment we created for Python. In the first cell, we're going to import the packages we need for our notebook. We're going to use some built-in commands for handling file names. We're going to use the datetime package for handling dates and times. We're going to use the NumPy package for handling arrays. We're going to use the RioXArray package for handling rasters. And we're going to use hvplot.xarray to make maps. To execute these lines of code in your notebook, hold down Shift and press Enter. Now we've imported the packages we need for our notebook. Now let's examine an ECOSTRESS Level 2 surface temperature image and a map in our Jupyter Notebook. First, we're going to define the file name for the image that we want to open. Then we're going to parse the timestamp from that file name. Then we're going to open the file using RioXArray.OpenRasterIO. This file includes scaled 16-bit integer digital number values, which we're going to need to convert into temperatures. In order to do that, we're going to use NumPy where, which allows us to use per pixel conditions. And the condition will be if the value in the data array is 0, we're going to insert a not a number np.nan value. And if it's not the fill value, then we're going to multiply it by the scale factor 0.02. And this will give us an array of surface temperature in Celsius, which we want to convert to Kelvin by subtracting 273.15. And we'll assign this converted array to the .data array of this surface temperature data set that we've loaded with RioXArray. And now to look at this image on the map, we're going to first reproject this image to the EPSG 3857 coordinate reference system used for WebGIS maps. To reproject, we're going to use .rio.reproject and then the coordinate reference string. To plot the image on the map, we're going to use .hvplot.image and then set the parameters for this map. The CMap determines the color scaling of the map. We're setting this value to jet, which will be a rainbow color map with low values being blue and high values being red. We're also going to select a base map using the tiles parameter, and we're going to set that to OpenStreetMaps with OSM. We're going to make the map layer semi-transparent over the base map using the alpha parameter and set that transparency to 0.7. We're also going to give a title to our map using the date and time that we parsed from the file name. And we're going to set the width and height of our figure in pixels. Now let's execute this cell by holding down Shift and pressing Enter or Return. Our first ECOSTRESS map in our Jupyter notebook has appeared, and we can see that we still have the cold cloud portions of the map that we need to mask. Now let's load the ECOSTRESS Cloud Mask product corresponding to the surface temperature image. Here we're defining the Cloud Mask file name with the same timestamp as the surface temperature image, but for the SDS Cloud Mask layer that we downloaded from Appier's. Again, we're going to open the raster using Rio X-Ray, Open Raster IO. To process this quality flag image into a cloud mask, we're going to access the data array of this dataset with .data, and we're going to bit shift this array 2 bits to the right, and then AND with 1, and this will produce a binary cloud mask. We're again going to use hvplot.image to look at this image on a map in our notebook. We hold down Shift and press Enter or Return, and now we can see our cloud mask on the map with the areas of cloud that we're going to mask out. Now, with the ECOSTRESS surface temperature and cloud mask images loaded into our notebook, we're going to combine them to produce a cloud masked surface temperature image. We're going to use numpy.where for a condition, the condition being if the cloud mask is true, then we set that pixel to the no data value, np.nan. Otherwise, we keep the surface temperature value. And then let's apply that and look at that on the map again. Now we can see that we've cloud masked our ECOSTRESS surface temperature image. Now let's apply the cloud masking techniques we've learned to process our batch of ECOSTRESS data we downloaded from Appier's. First, we'll create a new notebook to process our Farmington Summer 2019 data. We'll go back to New File and set a name for our notebook. Make sure the extension is IPYNB. And make sure that the environment is the ARSET ECOSTRESS Python environment that we created earlier. First, we'll load in the packages we need. Again, we'll use built-in packages for handling files, datetime for handling dates and times, NumPy, Pandas, Rio X-Array for handling rasters, RioXArray.merge for forming composites of rasters, hvplot.xarray for making maps, and matplotlib for making and saving figures. And we'll use Shift and Enter or Return to load these imports. Now we'll set some constants for our project. So the raw data that we will be processing is coming in from the directory we created to hold our app years files, Farmington Summer 2019 raw. We're going to write the processed files in the Farmington Summer 2019. We're going to use makeDirs to make sure that that directory exists so we can write files to it. And then we'll set some aesthetic options. For pandas, we'll make sure that we can see the entire table when it prints to the screen. We're going to set the transparency of our map layers to 0.7 and also set the width and height in pixels for our figures. We're also going to write a series of colors that we want for scaling evapotranspiration maps. These are hexadecimal values of colors in a list. Let's use Shift and enter a return to execute this cell. So to go about processing in bulk the files that we downloaded from app years, first we need to collect their file names. So first we're going to use glob to scan through all the files in our directory of raw geotiffs. And then we're going to insert that list of files into a pandas data frame. Then within that pandas data frame, we're going to parse each one of those file names into a date and time and insert that date and time into another column in that table. Then we're going to do the same thing for the cloud file names. Instead of searching for the layer LST in our geotiff files, we're going to search for the layer cloud mask in our geotiff files, and also parse the date and time from the timestamp in the file name. Then once we have these two tables with a matching column of date and time, we'll use pandas to merge these tables. And pandas will merge them using that matching date time column. Once we have that merged data frame, then we're going to construct the output file name for the file that we're going to write after we've done the cloud masking. And let's take a look at that table by executing this code with Shift and enter a return. So now we're ready to go about running through each row in this table, reading in the raw surface temperature geotiff, the cloud mass geotiff, and writing out the cloud mass geotiff. So now we want to iterate through each row in that table. And to access each row in that pandas data frame, we're going to use .iterRows. And then we can loop through each one of those rows with a for loop. So in each iteration of this loop, we'll have a new date and time, a raw surface temperature file, a cloud mass file, and the file that we want to create. So first we open the raw surface temperature file with rioxarray.openraster.io. Then we convert that raw surface temperature image into temperature by filtering out the fill value, replacing it with a not a number value, applying a scale factor to the raw 16-bit scaled integer digital number, and then converting from Kelvin to Celsius. And then we're also opening the cloud mask again with rioxarray.openraster.io. And then we want to make sure that this cloud mask is on the exact same spatial grid as the surface temperature. So when we open it, we also use .rio.reprojectMatch so that it matches the surface temperature image. And then we run the bit masking to convert this quality flag into a cloud mask. And then we apply that cloud mask to the surface temperature image. And now, as an additional step to filter out any pixels that were not recognized as clouds by the cloud mask, we're going to remove outliers from each image by calculating the quantiles. We're using NumPy nan quantile to calculate the 8% and 98% quantiles here. And then we're using NumPy where to replace any values lower than the 8% quantile or higher than the 98% quantile with a not a number, no data value. And then to make sure that we're only using high quality scenes in our seasonal aggregate, we're using NP count non-zero and NP is nan to quantify how many of the pixels in this image are missing. And if it's more than 50%, we're going to skip over this image. Once we have an image that we're happy with, then we're using .rio.toRaster and then a geotiff file name to write that image as a new geotiff. And then to make things easier, we're also plotting this figure and writing it as a PNG. Now let's execute this cell to bulk process our ECOSTRESS surface temperature images and write our cloud masked ECOSTRESS surface temperature images. Now let's utilize our cloud masked ECOSTRESS surface temperature images to form a seasonal composite for the set of summer 2019 images we collected from our peers over Farmington, New Mexico. So first we're going to scan for our cloud masked surface temperature geotiffs using glob. And then we're going to open each one using rioxarray.openraster.io. And then when we have this list of open rioxarray datasets, we're going to form a composite of those datasets with rioxarray.merge.mergeArrays. We'll give it the list of the rasters that we've loaded from geotiffs and set the no data value to np.nan. And now we're going to replace the data array in that composite data set with a median calculation using NumPy nan median. And we're going to run that median calculation on a stack of the data arrays from each one of these rasters using np.stack. Once we have that median image, we're going to filter out zero values with np.nan. And then once we have a clean composite image, we're going to write that to a geotiff using .rio.toRaster, and then the name of our geotiff. Here we'll call it Farmington ST Median Summer 2019.tiff. And then let's take a look at our composite on the map in our notebook. And let's execute this cell and take a look at our first composite. So here is our first seasonal composite of ECOSTRESS surface temperature over Farmington, New Mexico for the summer of 2019, aggregated by median. And we can see areas of cool farms in this image. And some portions of the agriculture are warm. Now let's also clean up the evapotranspiration images we downloaded from MapHere's. First, we're going to search for all of the files containing etinst in the file name. And then we're going to run a for loop through each one of those file names, parse the timestamp into a date time, and then we'll construct the output file where we're going to write our clean evapotranspiration image. Here we're opening the geotiff file of ET that we downloaded from MapHere's using rioxarray.openraster.io. And we want to filter out any values, erroneous values that are less than or equal to 0, and replace them with not a number mp.nan. For this product, the ECOSTRESS Level 3 evapotranspiration product, we do not need to do cloud masking because it's already cloud masked. And we also do not need to convert the units because it's already in units of watts per square meter stored as a floating point value. So here we're just filtering out any erroneous values. And we're also doing an outlier removal, filtering out lower than the 8 percentile or 98%. And again, if the proportion of missing pixels in this image is more than half, then we're going to skip this image. And again, we're writing this image, the clean image now, to a new geotiff using .rio.toRaster and the name of the geotiff we want to write. And then for convenience, we're also plotting this figure and saving that to a PNG file. So now let's execute this cell and generate our cleaned up ECOSTRESS ET geotiffs. Now let's take our cleaned up ECOSTRESS ET images and form a seasonal composite. First, we're searching for the geotiffs that we've written with ET, and we're opening each one of the ET files that we've written with rioxarray.openraster.io. We're forming a composite of these images with rioxarray.merge.mergeArrays. We're calculating a median of these images with np_nan_median, filtering out erroneous 0 values from the composite, and then we're writing our composite with .rio.toRaster and the geotiff name, which we'll call Farmington ET median summer 2019.tif. And then we'll take a look at this image on the map. Here we'll set the color scale, the CMAP value. Instead of being jet for a rainbow, we'll use the ET color map that we defined earlier here with these hexadecimal values. So let's generate our ECOSTRESS ET composite and take a look at it on the map. So here is our ECOSTRESS evapotranspiration seasonal aggregate, the median over the summer of 2019. And we can see that areas of irrigated agriculture have high ET values shown in blue here, along with the riparian areas along the river. And areas of non-irrigated land outside of the farms have low ET shown here in brown. So far, we've run this seasonal analysis on the ECOSTRESS Level 2 surface temperature product and the ECOSTRESS Level 3 evapotranspiration product. Let's also run this on the ECOSTRESS Level 4 evaporative stress index product. The evaporative stress index gives us a value between 0 and 1 that tells us how much the ratio of actual evapotranspiration, which we're seeing here, to potential evapotranspiration. Out of how much the plant activity there could be, how much there actually is as a proportion. So let's form a seasonal composite of this normalized form of evapotranspiration from the ECOSTRESS Level 4 product. First, we'll filter through the files that we downloaded from ET and search for the ESI AVG layer using glob. And then we'll use a for loop to loop through each one of these file names. We'll parse the date and time from the timestamp in the file name. We'll construct the file name that we want to write out. We'll open the evaporative stress index image from the geotiff using rioxarray.openraster.io. Now, since the valid range for this index is from 0 to 1, we want to filter out any erroneous values in the file that are outside of that range. And we'll also do some outlier removal by calculating our quantiles again, just like we did for surface temperature and ET. And also filter out any images that are more than half missing. And then we'll write out our ESI, our cleaned up ESI file to a new geotiff and write a preview image. And let's execute this cell to filter through our evaporative stress index images. And finally, let's take our cleaned up evaporative stress index images and form a seasonal composite of evaporative stress index. Searching for the ESI geotiffs that we've written, opening them with rioxarray.openraster.io, merging with rioxarray.merge arrays, calculating median with numpy nan median, writing the geotiff we want with .rio.toRaster, and then plotting a map with hvplot image. Let's run this cell. and look at our evapotranspiration index composite. This is very similar. This level 4 evapotranspiration index has a very similar spatial pattern to the level 3 evapotranspiration, but it's slightly different because it's normalized. We can also see that areas of irrigated agriculture have a high ESI. The actual versus the potential is a very high ratio. And then areas outside of irrigation tend to be lower. Now we want to repeat our analysis for summer 2020 and 2021. To submit a new request, we're going to go to Extract and Area. This time, we're going to copy a previous request here in the middle. We'll click on our previous request to open a copy. Now we're going to alter the start and end date. So our new start date is going to be July 1st, 2020. And our new end date is going to be September 30th, 2020. We want to keep the ECOSTRESS layers the same, the projection the same. We want to keep our same bounding box around Farmington, New Mexico. Before we submit, we'll give our new request a new name. This one is Farmington ET Summer 2020. And we'll go back down to the bottom and click on the blue Submit button. Now with our modified request still open, we're going to modify it again one more time for summer of 2021. We'll modify the start date to July 1st, 2021. And the end date will now be September 30th, 2021. And we'll update the year in our title. And we'll go back down to the bottom and click Submit again. Now we'll check on the status of the request that we've submitted. We'll go to the Explore tab at the top. We can see our previous completed request is still here, and now our two new duplicate requests with different start and end dates are still processing. Now let's repeat our summer aggregate analysis at Farmington, New Mexico with the 2020 and 2021 data requests we made. And at Peers, we'll go to the Explore tab at the top. And then we can see that our 2020 and 2021 requests are now completed. In our 2020 requests, we're going to download with the middle blue button on the right of the request. Click the checkbox at the top left, and then the download menu on the top right, and download files. We should organize the raw ECOSTRESS geotiffs we downloaded from Peers for 2020 into a new directory in our project folder. We'll call this Farmington Summer 2020 Raw. Now let's download our final App Years requests. Explore tab up at the top. Our completed Farmington ET Summer 2021. The middle blue button on the right to go to the download page. Checkbox at the top left. Download menu at the top right, and download files. We'll also organize the 2021 images we downloaded from App Years into a new folder. Now that we have our project files organized for all 3 years, let's go back to Visual Studio Code and reproduce our 2019 analysis for 2020 and 2021. We can reuse our 2019 notebook by making a copy of it. We'll right-click on this IPyMB file, copy, and then right-click in our Explorer pane and paste. And now we'll rename this file for 2020. Now in this new notebook, we want to select our kernel for the Python environment we created for this project. And we'll change the directory and file names for 2020. Now to run this entire notebook, we're going to use the Run All button at the top. Now that we've reproduced our summer 2019 analysis for summer 2020, let's reproduce this analysis one more time on the 2021 files we downloaded from App Years. We'll duplicate our notebook one more time with copy and paste. Rename our new notebook. select our kernel for our new notebook. And change the year from 2020 to 2021. And now we'll run this notebook with run all. Now we've reproduced our analysis again for our third year for 2021. Finally, let's bring this all together by plotting a time series of the summer aggregates of surface temperature and evaporative stress index that we put together from our ECOSTRESS data. Let's create one last notebook called Farmington Time Series. .ipynb. Make sure we're in our Python environment. For this project, we're going to use NumPy, RioXarray, and Matplotlib. We are again going to use our custom color map for evapotranspiration. And to make this compatible with Matplotlib, we're going to use linear segmented color map. To generate our time series, first we'll load in each of our surface temperature images from the summer of 2019, 2020, and 2021 using RioXarray.OpenRaster.io. Now we want to calculate a minimum and maximum value to display on all three maps together. So we're going to take all of the values from all of our images, stack them together, and calculate the 2% and 98% quantiles. We're going to do the same thing for our evaporative stress index images from 2019, 2020, and 2021, and also calculate a stretched minimum and maximum value. Then we're going to set up our plot using Matplotlib subplots function with 2 rows and 3 columns, and we'll set the color and size of the figure. And this will give us 6 panels to arrange our surface temperature images on the top row and our evaporative stress index images on the bottom row. And then for each panel, we'll use the .plot function from the dataset we loaded with RioXarray. we'll set the axis for it to plot to one of the axes supplied by the subplots function, subscripted by zero-based row and column. For the surface temperature images, we'll use our jet color map. But for the Vmin and the Vmax, we'll use the quantiles we calculated collectively from all three images, and we'll supply this same Vmin and Vmax to all three plots so that they're scaled in exactly the same way, and we can notice changes in temperature throughout the time series. On the bottom three axes of this plot, we'll do the same thing for evaporative stress index, but the color map we'll supply is our custom color map for evapotranspiration. And the Vmin and Vmax we'll supply are the quantiles we calculated across all three evaporative stress index images. And then once we have this plot in memory, we'll both show it in our Jupyter Notebook and we'll save it to a PNG file. So now let's run the final plot of our project. So here's the final figure of our project. We have a PNG copy of this as well that we can look at full screen. So we see in the top row our time series of surface temperature for the summer of 2019, 2020, and 2021. We can see that in 2019, it was a rather cool year compared to 2020. In the bottom row, we have the time series of evaporative stress index corresponding to these surface temperature images. We can see that in that cool year of 2019, when the area outside of the farms is somewhat cooler, the evaporative stress index is higher because there is more ET. And in 2020, when this area outside of the farms was warmer, the evaporative stress index was much drier. And in the evaporative stress index, we can see changes in which farms are wetter or drier from year to year. Utilizing ECOSTRESS data in such a way will help us to better monitor and manage agriculture and natural resources. This concludes our demonstration of utilizing ECOSTRESS surface temperature and evapotranspiration for monitoring agriculture.
Thank you so much. Thank you, Gregory, for such a detailed and wonderful demonstration of how to actually download and analyze ET from ECOSTRESS. And I just wanted to share this slide with everyone. We have a question answer session now. So please enter your questions in the QA box, and we will answer the questions as they were received in the order they were received. And the QA script will be posted on our website. You'll be able to see the question answers later. Also, here is the contact information for Gregory. If you have any specific questions, if you have any general questions, you can contact me. The training webpage is shown here. You will have the recording available here in next 48 hours. Here's the ARSET website for information about future training and everything. So what we'll do is now switch to our question answer session, and let's see. Okay. So question 1 is, I would like to know if ECOSTRESS data is available on cloud computing platforms such as Google Earth Engine, just like Sentinel-2 and Landsat SR data. Gregory?
Hi, yes. So EcoStress is not available yet on Google Earth Engine, but we're working on incorporating EcoStress Collection 2 data into Google Earth Engine and OpenET. And EcoStress Collection 2 will also be available on the LP Cloud environment through HTTP and S3 URLs.
Great, thank you. Second question is, can we aerially subset the data product of our interest in appears using the latitude and longitude of the corner points of the rectangle similar to Earth's data?
So I think if you want to precisely define specific coordinates for your area, then you should use, you should create a GeoJSON or a shapefile and then upload that file into the Appears request instead of using the box or polygon tools on the map.
And the third question is, why do we need Mamba? Can't we directly install the required packages using pip or conda, or directly run the notebook in a browser?
So we're using Anaconda because the Conda Forge channel in Anaconda is the most comprehensive repository for geospatial Python packages. And then unfortunately, the Conda command for managing packages itself is sometimes very slow. And the Mamba stand-in for the Conda command runs much faster. So I recommend using Anaconda with the Conda Forge channel and the Mamba command to manage packages.
Great. Question 4 is, I'm trying to download data for South Africa. I didn't get the drop-down options of data products in Appears. Any reasons why this happened? Is EcoStress only available in the US or South America?
Yeah, so EcoStress is available globally and it's available in South Africa. And then when I saw that question, I tried going to make an Appears request and drawing a bounding box in Namibia and search for EcoStress, and I was able to pull up EcoStress products and add layers to the request. So if you're having an issue, a technical issue using Appears, then you should reach out to the LP DAC team regarding your technical issues.
Question 5 is, can we access the script file after this training?
Yeah, so unfortunately, I can't make those actual notebook files available yet. I'm trying to get them cleared through release at JPL, and then I'll keep you posted how that goes. And I made the video so that the walkthrough in the notebooks goes slow enough that you should just be able to pause when you're looking at one of the chunks in the notebook and write similar code in your own notebook. So you can use the video as a reference.
Yeah, so the demonstration itself is, as Gregory said, it's slow enough that you can follow and make your own code, just using that as a reference. So that's the best thing to do for now before it actually gets permission for release. Question 6 is VSC better than Jupyter notebooks for processing geospatial data?
Yeah, I find the Visual Studio Code is a bit cleaner and it's a more all-in-one solution to using Jupyter notebooks rather than running Jupyter Notebook or Jupyter Lab from the command line, because it's the VS Code app handles running the Jupyter server and managing the Python kernels that run in Jupyter server internally. And you can just run it straight out of the box with VS Code with little experience.
Great. Next question is, When we selected the data format, we selected GeoTIFF, and an image for data and variable was downloaded. If we select the netcdf format, will it download a unique file for each variable?
Yeah, so ECOSTRESS on Appears is only available in GeoTIFF format. The Appears request form has a netcdf option, but it doesn't work for ECOSTRESS.
Question 8, the ECOSTRESS index was described as actual evapotranspiration to potential evapotranspiration. Is this PET for a reference grass, such as in Penman Monteith implemented for a grass using FAO 56 specified parameters, or if it is supposed to be the PET for the actual cover type present, where did this come from?
So the potential evapotranspiration that we're calculating here is using the Priestley-Taylor equation, which is equation 1 in the ECOSTRESS level 3 ATBD. It's not exactly the same as reference evapotranspiration. You could reach out to Dr. Joshua Fisher, the inventor of this method, if you would like further details on the nuance.
Yes, so here is the link for the ATBD document, and you will find reference in there too. The important thing, like you noted, it's not exactly same as reference ET. Question 9, is the climate of Farmington, which is semi-arid, a reason for the irrigated agriculture sticking out so much? Would you expect similar results in a humid climate?
Yeah, I selected Farmington, New Mexico for this demonstration because it was a good visual candidate. Because it's irrigated agriculture surrounded by an arid landscape, so that usually has a very high a very high contrast in temperature and evapotranspiration.
Thank you. So ECOSTRESS data is available for northern Mexico. Do these data have the same accuracy as USA information?
Yes, ECOSTRESS is available globally, and the ECOSTRESS Collection 1 evapotranspiration product that we're using here was validated using the FluxNet ground observations.
So question 11, is it possible or scientifically acceptable to compare ECOSTRESS ET-P to ETA to Penman-based land-measured ET0 and ETA? For our local area, flux measurements are difficult to obtain, but climatic data to calculate ET0 comparatively easy to obtain.
Yeah, and similar to the earlier question, the Priestley-Taylor PET that we're using here isn't exactly the same estimate as reference evapotranspiration, and you could reach out to Forrest Melton and Joshua Fisher to discuss that nuance.
Is there any limit to downloading data from Appears? Can we request a large time period of the ECOSTRESS dataset, or is it recommended to split our request into small periods?
Yeah, Appears imposes data volume limits on each individual request, so you can try making your main request as is, and then if it gets denied, you get like a little red message up at the top saying that it was too much to request at one time. So then you just have to split it up into years or seasons or something like that, and then keep changing the dates in the boxes and submit several requests instead of one.
Next question is, are the results of the ET product in daily values such as millimeter per day?
No, everything that we're looking at here is watts per square meter instantaneous ET. There is a daily average ET that's also in watts per square meters, which you would have to convert to millimeters per day. For ECOSTRESS Collection 1, The upcoming EcoStress collection 2 will have a daily millimeters per day layer.
Question 14. If we create an AOI with a shapefile or GeoJSON, what coordinate system projection do we need to use?
Probably best just to stick to WGS84 latitude and longitude. I'm not sure if I've tried using projected coordinates in an app years request. You could reach out to the lPDAC for further questions about app years.
Question 15 is, there are some limitations for the extent in appears. How to cover a large extent?
Yeah, so it's similar to the previous question. App years imposes some data volume restrictions on each individual request. So if you try to upload a shapefile of the entire, like requesting the entire planet at once, then it might say it's too large. And then you might have to break that up into like continental scale requests or something like that.
Great. If you have any more questions, please type them in the QA box. So one more question. Is it possible to apply an example where there is binomial, it should be, or rainfall distribution,
Or
irrigation, and can we use ECOSTRESS for long-term ET projections?
I'm not entirely clear on what the question is asking, but yeah, if you're looking at seasonal or annual aggregates of the EcoStress ET product, that could be useful for comparing to precipitation for hydrology.
So I guess what you say biennial, maybe that's what it means, that maybe ITC is going back and forth and you have two rainfall without irrigation. Can you use EcoStress for long-term ET projections?
Well, it's the EcoStress is it's an estimation based on an observation in hindsight. I'm not exactly clear what you mean by using it for ET projections, but yeah, I think at least a seasonal temporal scale, if you're making seasonal or annual aggregates of EcoStress ET, you could utilize that information for modeling projections as an input to a projection model.
Great. Next question is following up to question 9. Is there any additional masking required when the contrast between irrigated and non-irrigated land cover is not as great, i.e. humid southeastern United States?
We don't include any quality flags that would let you, within the product, that would let you distinguish irrigated land from non-irrigated land. You would have to get CDL or some data set defining where the boundaries of farms are if you want to do that.
So this is my conjecture here, is that because in the humid region, PET would be high too, right? And so maybe there will be enough gradient between irrigated and non-irrigated area. Because there's not enough water availability in non-irrigated areas. So evaporative stress, if you look at, you might be able to see the difference between irrigated and non-irrigated area. That's just my
Yeah.
here. Question 18 is, what is the resolution of the PET product?
All the products are 70 meters.
Okay, so next one is, why does the water in ET appear as Na? Yeah, not applicable.
The ECOSTRESS Collection 1 algorithm that we're looking at here does not process water surface evaporation. The upcoming ECOSTRESS Collection 2 products will.
Great. Thank you so much. Thank you, Gregory, for such a
Thank you.
demonstration and for your time and effort. And thanks everyone for attending today's session. We are almost at the end of the time. We will see you next week at the same time, where we will actually go through some exercises, basic exercises, just to get the data and visualize and compare. So that will be our last session on 15th of June. And we want to thank all of you for attending today's session. We also want to thank our ARSET team for their help and support. Brock Blevins, Sarah Cashel, Sean McCartney, Sabine Hudson-Odoi, Jonathan O'Brien, and Erica Potes. They all helped with this webinar organization. So thank you very much. Thank you all. And we will see you next week at the same time. Thanks, Gregory, again.